Today we'll talk about innovative building envelope systems. Now, when we talk about innovations, there are some factors that drive innovations. And today we'll look at the components that drive innovation in building envelopes, which are generally trying to achieve comfort conditions within an indoor space. When we look at a building, what do we look at on a much broader scale? It's an enclosure which is trying to keep you protected, be structurally sound, but it also separates the outdoor environment to the indoor environment where you're trying to achieve a comfort condition, try and keep you protected from the external elements. Trying to identify comforts. Now, obviously, as our body reacts to its immediate surrounding in order to achieve comfort, and our body reacts to it. So there are a number of conditions where you try and keep yourself comfortable. It's either through heat loss or you're trying to keep yourself insulated. We talk about a number of them in technical discussions like conduction, convection, radiation, and we try and keep ourselves cool by evaporation. There are two other factors which are very critical to comfort conditions. One is air motion and obviously the relative humidity in the indoor space. When we try and map comfort, my colleagues from HVAC industries might be familiar with this diagram. This is a psychrometric chart which maps temperature against humidity. And what you see as the little green patch is where the comfort lies. So if you try and map all the way from 20 degrees to 120 degrees Fahrenheit and try and map relative humidity from 20 to 100%, you get a little small patch where you can feel that, this is where the comfort conditions are. And that's within temperatures of 20 to 25 degrees C and a relative humidity of 30 to 70%. Now, what you see as a yellow dot on the right was the hottest day in Delhi last year. And what you see on the left as a blue dot was yesterday's temperature. So if we really have to bring that within the green zone, you have to use dehumidification or humidification technologies and in order to heat or cool a space. Apart from these factors, there are other conditions like what you're doing inside a space, whether you're in a sweatshop or whether you're sitting in a nice air-conditioned cabin, which talks about metabolism and activity level. How much clothing you are on, like I'm feeling really sweaty in my suit right now. Whether there's enough air movement in the space to make you feel comfortable, and equipment. If you're sitting right next to your computer, you'll obviously feel a little warmer than you would normally would. With these, we've seen the past 3 decades, buildings have changed. There's this aspiration of getting more glass out there to enjoy better views to the exterior and bring more light in. But obviously, that has consequences. You also bring in more heat. You try and put excess load on your HVAC systems. So the industry responds. There have been parallel innovations in products where industry has responded with thermally efficient composites. You have warm-age spacers in your IGUs. Coatings on performance glass has improved the performance of glass substantially. Relatively new, but really interesting is self-shading glazing units, where you have shading elements integrated in your glazing units itself. You have thermally bridged systems and improved infill, which improves the U value and shading coefficient of glass. But I mean, if you look at these, where do these innovations come from? Obviously, you want more glass. You want your building to have a much larger window. So the industry responds as a reaction to what products they can come up with and where does their R&D lead. So these are more reactive in nature. But if you look at innovations to take it a further mile, you have to use these technologies in a much wiser application and a much more intelligent application to make innovations more proactive. We look at some examples of where do these proactive changes, what kind of innovations these proactive approaches bring. The first example is a commercial building in Singapore, which started off as the architectural concept was to actually do a double skin, but a lot of our colleagues here would there's a constant debate about doing a double skin facade in tropics is not that effective to bring down your comfort conditions, to improve comfort conditions in the indoor space, and obviously has cost implications because you need to have a certain gap between your outer and inner skin, makes it more difficult to maintain. Atrium in Singapore, the building that's on the screen, utilizes an internal vented cavity, which utilizes the indoor air, moves up the cavity inside, and then heads into the plenum once it's fully warmed up, and that's utilized by the air conditioning system. So instead of having return air separately identified into your ceiling, you take that right to the edge, you heat the air up, and that gets recycled through the air conditioning system. The next example I have is the library. It's a public building in Singapore. And one of the examples where the government really wanted this to be a benchmark in green buildings. And this was the first Green Mark Platinum building in Singapore, designed by Professor Kenneth Yang. The National Library utilizes a lot of shades, and shades move beyond just being traditional shading, but they also extend into the indoor space to increase daylighting. And this building was able to achieve its daylight mandate of 250 lux indoors on a good day. The shadings just don't go with built spaces. The building block consists of two separate building blocks, and there are shades that actually bridge between these two spaces, and they shade up the laneway below, which utilizes the public space. And this was a really big engineering challenge for us to be able to make them viable. It spans about 16 meters, and it's only about 400 mm deep. So we had to use restrainers, we had to use tiebacks to actually bring it back to the building. Makes it look more like a World War II aircraft, but it really works well. The next example I have is a building that was recently completed, and it's a biome, it's a public building, it's a greenhouse, and it actually utilizes a lot of green features right from the building design as well. The form of the building is shaped as an ellipsoid, which is tilted towards, go to the next slide, which is tilted towards the sun, the path of the sun. So you actually expose, you try and minimize the exposure to the sun, but what takes it beyond that is an intelligent array of shading systems which go on top of the building in form of triangular sails, which are deployed by motorized actuators, which are tied back to the building maintenance systems. On a really good sunny day, you could have a lot of light penetrating through, which may make the space uncomfortable for people using it. The shades deploy on its own based on what the building information system feeds it back to the deployment systems. The next example I have is of Abu Dhabi Industrial Council building. This building also utilizes dynamic shading. Now the issue with dynamic shading is that a lot of moving parts, a lot of motorized parts lead to failures, and maintenance becomes a large part of the post-handover period. What's really intelligent about this building is it actually utilizes an Islamic concept of mashrabiyah, which then translates back into a single working component of a triangle, which gets actuated with a single hydraulic jack, which is situated in the center. So what you see on the right is a partially open shading device. And as the sun moves around the building opens partially or is completely shut in order to save on the heating, the cooling loads of the building. These examples address shading, which talks about heat gain. The next example I have is a public piazza in Singapore. And with these examples, I'll start talking about ventilation, intelligently ventilated buildings. Now, when you talk about a public piazza and you have to make it comfortable in tropical climates, what you would ideally do is you would completely encase it in a glass shell on top, which brings in light, provides you the sky views, and throw some air conditioning in. But the project that you saw in the last slide is in Singapore. The temperature does not fluctuate a lot, does not vary a lot. What could be done intelligently is to actually shade it and then provide the sufficient air movement for you to create comfort conditions on the ground level. So what Clarkey does is to actually utilize an umbrella, which is on the outside, have fritted ETFE, have fritted ETFE on as an infill material on top, which brings down the solar radiation reaching the ground by 40%, and has these ventilators, has these mechanical ventilation system, which is unidirectional, so it actually channelizes the flow of air through the piazza, which helps achieve 5 to 6 meters per second of airflow on the ground. Talking more about ventilation, the next example is a residential building in Singapore, which is not an Arup project, but I thought it was very valid to put up on this platform. The problem with high-rise residential buildings, I mean, anything above 15 stories, is how do you naturally ventilate it? The first problem is high wind pressures that you have at that level. And can you actually open a window? Can you really open a window at that level? So the way Moulmein Rise addresses that problem is by having an interplay of 600 mm between your structure, where you pull your structure back, and have this space to play with two different window configurations. One is where the window is actually flush with the structure, and second is where the window is pushed out. So you actually create a ledge which is operable, which can be open, and you can actually leave it open for purely ventilation purposes, or you can even have a view down. They named this a monsoon window, which actually has won a few awards. The next innovation I have is from our Berlin office, where they've actually tapped on natural processes of photosynthesis to generate heat, which is very critical in buildings in Europe. What they have done here is to actually encase active algae in between two sheets of glass with conductors in it. And when it receives, even in the conditions of diffuse light, and the process of photosynthesis actually generates heat, and that heat is channelized into heating buildings, the internal heating system. In conclusion, well, I think most of the speakers so far have highlighted this, that you need to have a holistic design intent where the architecture needs to respond to these needs. And we need to integrate new technologies, not just run with the technologies, but also look at smart applications of such technologies. And that's the end of my presentation. Thank you.
Thanks, Gautam. In fact,